Today we're going to do a training over slab and wall analysis and design. As you can see in the image, our structure will be mainly composed of slabs and shear walls, although we also have some columns on the inner part of the building or in the center part of the building, and that's mostly just in the end we'll be showing some of the different kinds of testing you can do on the slabs, and one of them will be shear puncturing testing, so that requires columns instead of just regular walls. So that's the reason we've included them. Here are the dimensions of our building. So we have a 4-story building, almost 9 meters high and about 24 meters wide. You can see that the slab is slightly, I guess, bigger than the rest of the slabs. So we'll have a raft, which we'll call the, where we have the, I guess, first floor, if you will, and then the rest are just regular slabs. Here are the sections that we will be using today. So we are going to have, as I mentioned, some columns, and the rest, these girders are basically like the outer boundaries of the slab and of the raft. And lastly, we'll have what we called a wall marker, but you can see it's very small. Actually, in the end, we'll end up replacing it out of the model anyways, but these are going to help us from the modeling point of view when we're importing layers from a DXF file. We'll be assigning these individual sections, and it'll make it easy for us then to mesh an area, a closed area, with these girders in place. But most of what we'll be analyzing anyways will be will be based on these 3 elements here. So the raft will be the thickest, the walls, and then the slabs. So these materials are all the same concrete. It's by this grade, but in the starting file and the effort to save time, we'll already have these defined. So I'll show you where you can, if you wanted to manually define these 3 types of properties. But just keep in mind, in the start file, if you do download it and want to try it on your own, these are already designed. So we're going to be basically importing from the same DXF file 3 main layers, which will be the wall layer, the raft layer, and the slab layer, and we'll do these individually and then just assign, as I said, either markers or the outer boundaries, like these thin girders. And then from then on, we'll just model the rest of the structure by using commands all within Midas Jen. Some of them will be just extruding these columns or extruding the walls, and then using other features like auto mesh. But from here on out until we get to the end, I will be basically just working within the model itself, switching a little bit back and forth with the presentation just to highlight some points. But let me just go ahead then and open the program. So this is Midas Jen. If you've been following our series, you're a little bit familiar with the distribution of the commands. So just quickly to oversee, as I had mentioned in the workstream, which you can also explore over here in what would be properties, is where you can find the 3 commands to define or 3 windows to define the material, the sections themselves, and the thicknesses, which you can also see here in the workstream. As you can see, they're all in blue. That means that none of them have been assigned to anything yet. And so if you were to modify this or wanted to modify this or just explore it, you can right-click directly in the workstream, or you can just go to the window icon. And both will get you to the same section, which is basically where you can define dimensions, or you can also from a database select the particular section in and on itself. And you can also change the offsets here. So as I mentioned, we'll be starting by importing what would be these DXF files. So this step right here. So let's go ahead and just open the DXF file that's also part of the starting files we include if you download this material. So we'll go to import, and we'll go to import the DXF file, basically an AutoCAD file. So the way you would set this DXF file in AutoCAD would be just to assign individual layers for each of the different things you want. So as you see here, we have the three main ones that we care about. So when I select the, for instance, wall layer, I can just bring that over and assign a particular section to it. So I'll use the markers section for it. And you see that basically it just outlines for me where these locations are. And it'll make it very easy for me when I'm modeling within the program the real walls. So then I'll just undo this and follow the same for each. So the raft will also have its own, this time it has its own girder. We see there. And finally the slab has its own section or girder. So you see how now we have the basic outline, we know where things are laid out, and also within the workstream, I can now select individually directly from here. So it makes it much easier now when we get to the next steps, which will do a series of extrudes and meshing of the raft elements. So we'll start off by actually extruding the columns. So for that, I'll just go to the tab that says Node Element. And we see here we have all kinds of commands, similar concepts to what you would think in, AutoCAD kind of programs. So you can move something, like translate it, or you can divide, extrude is what we're going to be working with. And then eventually we'll also work with the auto mesh. So we'll start off by just extruding our columns. From the presentation itself, you would be able to see that we're only going to select, or if you recall, the inner nodes. So I'm going to change my view over here to top view, or you can do Control-Shift-T. And the method I'm going to select, the extrude type will be node to line element. So I just have to select the nodes of interest and assign the section. In this case, it's the column section. So I'm going to select here the select single method, and I can just draw to capture. It doesn't matter if I'm including the elements, which are the lines. What the program is going to do is just select the nodes and extrude those based on my selection method or extruding type method. And then I would just give it a distance and a number of times. So in this case, I'm going to give it a negative, since I want it to go down, 2.8. And if you notice, I'm in the DC, so in the vertical area of the coordinates. And I can just go to apply. And we see there now these columns have been created at the location of these nodes. So that's the first step. Now we're going to go and mesh the first floor raft. Sorry, the slab, first floor slab, which would be this part right here. So we'll go here to Auto Mesh. It's a nice little feature of the program that it does allow you to connect any kind of regular geometry as long as it's like a closed boundary by lines. You can select if you want it to be quadrilateral elements, triangular elements, or both. And you can assign the thickness. Our slabs will have a thickness of around 15 centimeters, so we select the 0.15. And then we just click in here and draw a rectangle from having like a front view. And we make sure only to capture the nodes, but also include the nodes of where the walls are going to be. And we're going to give it a size of 1. So that means that basically the square elements that are created, or quadrilateral elements created, are more or less have a side of 1 meter. So it's a 1 by 1, more or less. You see that in some, of course, irregular sections, there will have to be some other, triangular or irregular shapes to make that work. And you'll also notice that if there's an opening, it will leave it open. If you want to also mesh that, you can just activate this option here called Mesh Inner Domain, and it will mesh everything. But in this case, we want to leave that opening, call it an elevator shaft or whatever, just as a, showing you what the different options for these meshes are. So now we're going to create the walls by extruding them. We will go back to extrude. And this time we're going to select a different method. We're going to select from line to planar element. The thickness that we're going to assign to this will be actually 20 centimeters, 0.2 meters. We see we have two types. We can select thick or thin. It's a little bit internal calculation difference within the program. So you can consider thick is everything you most likely see in a structure. So your walls, if you will definitely be considered thick. Thin would only be applicable for something like if you're doing some sort of like metal storage tank or something like that, where it's more of a thinner metallic, planar element kind of thing. But for most purposes, especially we're using concrete, you just select the thick method or a thick type. I'm gonna now try to select the basically sections or the lines that correspond to a wall. What we can do is we can use this feature in the program is that I can open a second work tree by right-clicking right here on this boundary and activating this option that says Tree Menu 2. And now if I go to Works tab, I can select directly from the sections the one that I had assigned when I imported from AutoCAD. So we maybe it's not a good contrast because the slab is orange, but the lines have been turned red. They've been selected. And here again, I would just give it the same distance that I did for the columns, which is the height of the first floor, or 2.8 meters. So we see there now these have been created. And the last thing would be then to mesh the raft. So I'm going to change the view to just show not the thickness or the sections assigned, but just like the nodes and the sections, just to make it a little clearer. So we're going to go back to Auto Mesh. And again, we're going to select the method line elements. We'll use the same thickness, the same size, but this time the thickness is for the raft, which is about 30 centimeters, 0.3. And I'm going to do from view, and I'm going to just select from left to right a rectangle, all the bottom nodes, including the wall nodes, so they are also meshed connected, and the columns. So here everything will be connected together. So now we have everything up to the first floor, more or less meshed. If we want to get rid of the view of those blue nodes, we can go here to display and just deactivate that under the node tab. Makes it a little clearer. If we go back to hidden, you can kind of see the structure. So this basically lets you see the sections themselves versus just seeing like the elements, either planar or line. If you want to assign different colors or random colors, you can do that by going to the other display command here, display option, and then go to the draw tab. And here you can tell it by section or by material. Material wouldn't make sense for ours, but section and then assign random color and then apply. So you can keep doing that over and over. I mean, in some cases, when you first do it, everything will be a uniform, either gray or red color, but this allows you to more easily see where the different sections are distributed. And also, if you want to see the default is that you don't see the thickness of your planar elements. So if you do want to see that, you would just go to the other option that says hidden option and activate plane thickness. And that would allow you to see the thickness of your raft and your slabs and your walls and all that. Because by default, they're just flat. Okay, so now we're basically done with the first floor. What we're going to do is we're going to apply the pressure loads, and then we're going to extrude, make copies of this floor for the rest, the last 3 floors. So first I'm going to create the load cases. So I'm going to create 4 load cases. We're going to have the dead load. I'll select here from the list. We'll have the live load. And then we're going to have 2 wind loads in the different directions. So these are static load cases. We're additionally going to add a response spectrum to our analysis, but we don't create the static load cases in this case. That's considered dynamic. So we just select here the wind load, and we just give it two names. So we gave it WX, and I will do wind Y. So those are our 4 static load cases. First thing I'm going to do is just apply the self-weight to the dead load case, and I would just give this Z a -1. Basically, direction of gravity is working down. And then I'm going to apply basically the floor load. But because we're working with rafts, we've been showing in previous webinars, you usually assign them, if you had like a building with, just beams and columns and maybe just walls, but no slabs, then you could assign them by this method. But because we have slabs, we will assign them by a pressure load. And so we would just assign pressure load. The load case here will be live. We'll just we won't add any pressure loads to the dead load case. We'll just only do live loads to save a little time as well. And then here we'll just say 7 kilonewton per meter square as a pressure, but we want to give it a negative value. Again, we want it to act vertically down, and that will be displayed in the arrows once we apply the load. And so we're going to send it to the first floor slab. So there's different ways you could do this. You could just select the nodes by creating a rectangle over the elements like this, or you can directly from the workstreet, we already know that the slab is the one with this thickness, so you can also just select it from here, and then you can just apply it. And so we see here the arrows are pointing down and they're applied to all the nodes. So now what we're going to do is we're going to generate copies of the floor. And the reason we did this after the load is that when we generate the copies, the load will also be copied. So we don't have to do this every time to every floor. So we'll go to here to structure, control data, building generation. And so here you decide how many copies you want to make out of the elements you're selecting and the distance. So let's say we're going to make the next 3 floors and they'll be 2 meters each. So we would just go here to add, and then we select the elements we want to apply this to. So again, I'm going to do the from view, and I'm going to draw a rectangle this time from right to left, cutting through the middle of the walls. So what this does is this selects everything except for the raft, but I'm selecting all the elements like the walls and the slabs. And I just go to apply. So in this case, our structure has been copied. And if we were to tell it to show us display the pressure loads, those were copied as well. So now what we're going to do is we're going to mesh the walls. So far we just extruded them, and they're these long planar elements. What we want to do is we want to create these meshes that have nodes between them, and we'll have it so that they're similar distribution, similar sizes as the slab and the wall elements, like a 1x1. So what I can do is I can just basically you could think of it as remeshing. I'll use the auto mesh feature again. This time the method is planar elements, and I can directly just select from here I already know the thickness of my walls, and only the walls was the 20 centimeters. So I can select it from the other work tree. And here, by giving it this dimension, I just make sure again that I'm giving it the same thickness. And this is basically going to break up my long planar elements into planar area elements, basically into meshed set. The reason we also waited to mesh the walls after we made the copies of the stories was that the stories are different dimensions. The first story is longer, almost by 30% than the other floors. But if you were just going to make copies of the floors all the same heights, you could mesh the wall first and then make copies. The sequence itself is basically of no importance. You can arrive to the same conclusion, except for, of course, as I mentioned, our first story was large, almost 30%. This is why if you give it a dimension of 1, you'll have 3 divisions, whereas in the rest of the floors you have 2. So we're trying to make the nodes evenly distributed or even dimensions. But the floors loads themselves, the pressure loads assigned, are not affected by this. So now we basically have the structure in place. We can proceed to apply other loads like the wind loads and the response spectrum case, dynamic case. But for that, the program needs a little bit of information about where the nodes are located, like the height of each floor. Sorry, I will go here to story now, and I can auto-generate this data. Basically, the program recognizes the height of each location of each of my floors. So even though there's nodes in between these floors, you want to select only the main floors. The program recognizes this automatically. So another reason to have meshed the wall after you've done the building generation. This is updated automatically like this. And you'll notice, relative to the previous cases we've done, where we assign the floors by basically the loads as floor loads, in this case, because we have slabs, the diaphragms are not considered. So those are the 2 methods to basically model your floor diaphragms. If you had beams and columns, then you can activate that diaphragm here, but since we have slabs, we don't need to. The other thing I'm going to do is I'm going to go to structure type, and I'm going to convert the self-weight into masses. Activate this. So now we can proceed to assign the wind loads. I'll go to load. I'm still under static, and I'm going to do here lateral wind loads. This is something we've been showing in previous examples as well, but we'll just include this quickly. So we'll first do it in the X direction, and you can select the different codes. This is the latest we have for ASCE. So we'll just do this category, and so the way you give it direction, first is the eccentricity. You can just activate positive or negative or none. And then here it's really the wind load direction factor. So since we're doing it first in the X direction, let's do X1 and Y0. We can actually check the wind profile here. And we can go to apply. And it's already created. So I can just select the last load case, which is the Y, and just basically flip this. And here is the critical one. In the X direction, it's now 0, and in the Y direction, it's now 1. Again, this is a factor, so 1 being the full. So we have our wind loads applied. And if I remove the hidden view and just show the nodes, you can see the icons of these loads as well. This is why we wanted them on each floor. And now lastly, we'll do the response spectrum. So we'll go back to load. This time it's under dynamic loads. And you see here we have the response spectrum function. Add. Here you can copy paste your own response spectrum function from any Excel table you like. Or you can also create one by selecting from the list of spectrums we have. So we'll just use the, again, ASCE, the 2010 is the latest one. And we'll keep this as is, but you can select different parameters and the program will create it for you. But again, you can directly copy paste this from your own Excel. And so once we define the function, then we just define the cases. We'll do one in the X direction and we'll do one in the Y direction. So for the X direction, let's just call this our X. We will leave the excitation angle at 0 and the scale factor at 1. We'll activate the function we selected. Here's where we can activate the accidental eccentricity. If you wanted to see more details about it, you can just click here and you can either do it automatic 5% or you can define it manually for each story or each floor. and then you would add it to the list, the load case. So we would go back and do the same for RY in the Y direction, and the only difference being that now the excitation angle is 90 degrees. So we basically only have to do that difference. And for this kind of analysis, we also need to have some specifications about eigenvalues analysis. It will also be performed. So here you can see there are different types. We'll stick to the Lansons, and we will do 15 frequencies. But you can do, there's 3 different methods you can do this with. And the last thing we would need to apply would be the boundary conditions. Now you could just apply some, if you wanted to make it simple, you could just define like some sort of fixed support in the bottom here. But the program also allows you to simulate what would be soil springs. So in this case, because we have a raft, no piles or anything, we can just select the surface spring. And you can directly input what would be the modulus of grade reaction. So you can just put in these values here that I'm getting from the table in the manual. And usually the XY springs are about 10% smaller than, or 10% of the value of the vertical spring, of the C spring. And we will apply it to the raft. So from the worksheet, I can select the thickness of the 30 centimeters since I know that's the one that I applied to my raft, and just apply. And so we can see here the icon for these springs that we've created. And so we can just run the analysis. We go here to perform. And we'll be getting information down here about the process, if there's any warnings. So this is the message window, which also gives you information as you're creating the model itself, if something doesn't apply, kind of like the wrong element is being used or something like that. You can get warnings here. So we see it's going now through the response spectrum cases. So first went through the case 1, which is X, and now it's going through case 2, which is the Y. So we see it's finished running, and my laptop, being a regular laptop, I guess like 6 gigabytes of RAM, took about 51 seconds, under a minute, if you will. Of course, this is only like a short story building, but it's relatively quick. So we can take a look at some results now. We go to the results tab. What we can do is create load combinations to when we see the results. So we can just go to auto-generate. We have basically concrete structure. So we select the concrete design tab, and we just go to auto-generate, and we can select the code we would like to do this for. And if we wanted to, we can inspect them or add our own combination of load, result, and give it a factor. So we can take a look at a few results. Like let's look at displacements for, let's say, the live load, which is the pressure load we applied. We can go here to displacement contour, select the load case. In this case, we'll do the live, and we'll do the XY. I'll activate the deformation, and here in legend, I'll click apply, and then I'll modify the legend so you see where the default is to give you the results in exponential format, but we can control that. So you see here, we see it as 2.5 to the -3 meters. So I can change these units to millimeters, and then just update it that I just wanted to see it in decimal, not in what would be exponential format. See, now it's 2.53 to the 0. So if I go here to this triple button, I can just tell it fixed and select the number of decimal points. and it's updated. So you can see other things. We've been, for the most part, working in previous examples with regular 1D elements, regular beams, regular columns. However, now we're working what would be plates. So if you wanted to see beam diagrams, in this case, they would only be available for results for the columns, since everything else is just a 2D element, except also one, I guess, for the girders around the slabs. So what we really want to see are the results for the slabs and the walls. So it wouldn't be beam diagrams, it would actually be plate forces, moments. So here, for instance, we can see the max axial forces, or you can select by direction. And you can update the units back to, in this case, kilonewtons per meter. Or, you can see the moments in the different directions. There are the maximums. So these are the structural results, like the forces and the moments. But you can also see the stresses for the plates. So we go to plane stress, plate stress. And for instance, you can see like the max shear, depending on which load case you're selecting. All these we've been looking at is the live load. So now what we're going to do is we're going to pass on to what would be the design aspect or capabilities of the program. But for the most part from here, you can see other things like reactions, soil pressures and such. Everything in terms of the results would be in this tab. But you can see even here the soil pressures created on your slab. This might be a little bit easier to see if you take the thickness out, undo the hidden view. And I guess also the reactions, you can see them here. So that was soil pressure, but you can also see the reactions for the different load sets. So now we go to the design tab. We're gonna go through some of the design features for these meshed elements, which are the walls and the slabs, including the raft. So for that, we would first have to tell the program which load combinations we want to include when it's doing the design or when it's doing the check based on the code and the combinations. So just to save time, I'm only gonna select the first combination for each set. So you see here that there are different methods for these designs, or as I had mentioned, checks. And so it all depends which one you're going to select, but for the most part, let's just, if you want to go through them, have at least one selected for each. We'll make just the first one. So I'm only having activated the first one of each option. And then we're going to specify information to the program about the rebar distribution, so design criteria for rebars. And we'll deactivate the basic rebar options, and we'll just manually tell it different sizes of rebar you want it to consider. You see we have different options, which you can, if you go to tools, options, you can select which of the, I guess, codes you want to use for the rebar. In this case, we're working with ASTM. And you would give it a little bit of information about the distribution of these. There is, in the manual, I guess a guide of where more or less this direction 1 and direction 2 are within the slab and the walls. Sorry. So we'll do 0.03 in direction 1, 0.05. So this is for the slabs. And then for the wall, we'll do the about 0.02. And we'll just leave the bar selected as is for the sizes. So then the next step would also be just to specify for checking. So we'll call this slab. We'll select from the work stream both the slab, sorry, that's the wall, unselect. Select the slabs, and if you right click, you have this other option that says here select plus, basically just add on to whatever you had selected. So we're specifying specifically the rebars, and we would do the same for the wall. So these being millimeters, and we select here. So now that we've specified information to the program on what information, or specified rebar information, we can now go ahead and run these designs and these checks. So we can go to design of the slabs first. And we see here when we do the flexural design, we have about 5 different options. We will do it by resistance ratio. In the tutorial itself, we go through a lot of details. It's almost like straight from the manual on what all these commands do in terms of averaging or in the results of the nodes, or is it per element, and what the different calculation methods are for each of these. So it would be, if you do go through the tutorial, you can get a lot more information. It can be a lot more clear of what these other options are and which one is you consider more appropriate for what you're doing. So we have, wood armament, resistance ratio by rebar as required by a certain area per meter kind of thing. So we will just do resistance ratio. So resistance ratio is the ratio of the design moment to the moment resistance where the rebar is applied. So these are all, as we mentioned, the ratio design moment versus the resistance moment. So we can do other kind of testing, not beyond these 5. There's also serviceability. So flexure, slab, serviceability checking. Again, within the PDF, we've included explanations from the manual on what these different uncracked, or if you want to consider the creepage, and the ratios for these as well. So because of all the planar elements, if you will, the meshed elements that have to be considered, these kinds of designs are a little bit slower than if you were doing beams or columns like we've done in previous cases or previous tutorials. So this is where those combinations that we had selected come into play, that you could have like selected. The next one will be the type of checking you can do would be the slab shear check, the punching shear check, and you can do it by different codes. You can do it one way or two way. And that's basically, it allows you to see where the slabs elements have the concentrated loads related to the columns. And you can check for along user-defined check lines. So we see here all the points correspond to where the slab meets the columns, and this is part of the reason why we included these columns in the first place, just to show you this feature that the program can do in terms of design or in terms of check. And then the last thing would be the wall elements. And again, we have similar methods that we had done for the slab, can also be done for the wall. And again, in the PDF, basically is the very clear description of the equations used for these testings based on the different options. So the program can give you, once you run the design, it can give you results, it can give you forces, and it allows you as well, based on those parameters, to update the rebar information, the distribution of the reinforcement, basically. But you can get these kind of reports. But that would basically be the, once I show you that, once the report is created, that would basically be the conclusion of the modeling we were doing today, the training session for today. In this case, I don't think it liked it that I was playing back and forth with the PowerPoint. But for now, basically, that's the conclusion of the training. So thank you very much, and I'll